are going to discuss one of the important topics in some basic concepts of organic chemistry. We have already dealt with the topic isomerism, in that we have learned structural isomerism and we also learned stereoisomerism. In the stereoisomerism, we have mainly learned geometrical isomerism. So the next isomerism that comes under stereoisomerism here is optical isomerism. That is very important. Okay, so you can give the heading optical isomerism. Okay, so the topic we are going to discuss here is optical isomerism. Okay, so this topic is simple. We should just understand and learn it. So with that we will be able to answer almost every questions. Okay, so what first thing we should discuss, what do you mean by optically active compounds? So you can give the heading optically active compounds. What are optically active compounds? Okay, this is compounds. Okay, so I can define optically active compounds as what? Actually, those compounds, okay, those compounds which rotate, okay, which rotate the plane polarized light, which rotate the plane polarized light, which rotate the plane polarized light when it is passed through them, when it is passed through them. Okay, when it is passed through them. So, and let's say, for example, we have a monochromatic source of light like this. Okay, so this is not a plain polarized light. This is aligning in different directions. So this is a monochromatic source of light. Now what we are doing is we will convert this into plain polarized light by passing this through a Nicol prism. So consider this as my Nicol prism. Okay, this is my Nicol prism. Now when it is passed through Nicol prism, this will get aligned in one direction. Okay, so let's say in vertical direction. Okay, so this is how the light will get aligned. So this aligned light, which is aligned in one single direction, in vertical direction, is called PPL, or plain polarized light. Okay, now what we are telling here, so now let us we can say we will pass this plain polarized light. Okay, so this plain polarized light, we are going to make this plain polarized light to pass through a particular solution. So this solution is what is our optically active compound. So I can say this is a solution of optically active compound. So optically active solution, optically active solution. Now when you are passing this light through this one, what will happen is, if it is optically active, this will get rotated either this, now you know that this is in 90 degree with this one, correct? So if it is rotating like this, some so in some if it pass through, maybe let me say this is optically active solution A. Now on passing the this plain polarized light through an optically active solution A, you could see this has rotated towards the right. It has rotated towards the right. So this type of optically active compound is called dextro, or it has resulted in dextro rotation. Okay, now suppose sometimes when we pass this through another solution, let me say maybe solution B, what will happen to this plain polarized light? This may get oriented towards another direction. Let me say initially it was with 90 degree, now it has moved in this direction. So it has moved towards the left, so it is called a levo rotation. Okay, now I can say here this how much it has rotated either towards the right or towards the left. This is measured using an instrument that is called polarimeter. What it is? Polarimeter. So what polarimeter will do? Polarimeter will measure how much it has rotated towards the right or how much it has rotated towards the left. Clear? Okay. Now we can say if the optically active compound is rotating the PPL towards right, we say this is dextrorotatory, or if the optically active solution, it turns the PPL towards left, this is plane polarized light. Okay. Towards the left, we will say it is levorotatory or L form. This is called L form and this is called D form. Okay. I hope this is clear for you. So we can say this plus and minus form isomers of a compound, they are called optical isomers. Okay, and this phenomenon is termed as optical isomerism. Now let's say another important term with respect to optical isomerism, that is called chiral center. Very important. So please give the heading chiral center. Chiral center. What is chiral center? That's what next we are going to discuss. Okay, so we can say chiral centers are those centers. Okay, we can write it down. They are those centers. They are those centers which create what actually? Which create unsymmetry. Which create unsymmetry in a molecule. Which create unsymmetry in a molecule. Okay, they are called chiral centers. Usually chiral centers must be very important point, must be sp3 hybridized, sp3 hybridized with different valencies. We will see it with different valencies. So that means for double bonded compounds or triple bonded compounds, we won't usually say it as chiral center. Okay, so let's say for example, now I am going to take one example. Okay, I hope you could see this. So this is one example. So okay, now can you tell me whether you know there are multiple carbon atoms are here? Okay, so let me say whether this carbon atom, what I am drawing here, this one, okay, whether it is a chiral center or not. So for a carbon to be chiral in nature, its valencies, 4 valencies should be different. Now if you see here this is CH2 and CH3. Okay, here also it is a CH3 and CH2, both are identical. So in that case I cannot say this as a chiral center. So I can say it is not a chiral center. Not a chiral center. Now let's take another one. Suppose if it is like this, I hope you could see it. Okay, now so you have something like this. So can you tell me this carbon is a chiral center? Now you can see here CH2, CH3 is present. Okay, so this is a different valency and this is a CH2OH, that is fine, but there is a cyclic ring between the other two valencies and we can find a plane of symmetry between in this cyclic ring. Both half is similar, so we can say again this is not a chiral center. Clear? I hope this is also clear for you. Now let's take one more example. Now you need to tell me. Okay, this is another good example, almost similar to this one. So you have something like this. Okay, right, and you have valency like this. Now can you tell me whether this one, what I am taking here, is a chiral center or not? So we will see here CH2. Okay, here also CH2 and CH3. This is propyl group, and here CH2OH is present, and the next one both are ring, actually connected to the ring, and we could find that both half are different. This half is not same as this one, so I can say this is a chiral center. This is a chiral center. Very, very important. So simply speaking, I can conclude saying that if you have a carbon, its four valencies, let me say A, this is B, this is C, and this is D, are different. That means A should not be equal to B, and B should not be equal to C, and C should not be equal to D. In that case, C is called as a chiral center. Clear? So I hope this is clear for you. Now next we will go to the next concept. Okay. Yeah. So now let me take one more example. I could see more examples here. So what about this one? CH3, CH2. Okay. This is connected to a carbon, and this is connected to CH3, and this is connected to OH, and this is connected to hydrogen. Now I know that this carbon is not chiral because all three are hydrogen atom. Here two hydrogen atom, here three hydrogen atom, but this one is chiral because one group is CH3, another group is OH, and another group is hydrogen, and the next group is ethyl. So all are different. So I can say this is a chiral center. Clear? Now let me take another compound. This is a good example. Suppose if you have a question like this. Now here you could see bromine atom being connected here, and here also you can see bromine atom being connected here. So can you count and tell me how many chiral centers are there? So if you see one by one, so here if you see, you know, this is a carbon atom, but here you know both are hydrogen atoms, so this cannot be a chiral center. This one, if you see here also two hydrogen atoms are there. Whenever two valencies are same, it cannot be a chiral center. Here also one is hydrogen atom, other is also hydrogen atom, and here also it is hydrogen atom, and here is also it is hydrogen atom. So all these are not chiral centers. But when it comes to here, one is bromine, okay, one is bromine atom, then the other one is going like this, and other one is going like this, and the fourth valence is a hydrogen atom. Now we know the other two are connected to a ring. So if we are trying to find a symmetry in the ring, we cannot find it because this half, what I am drawing here, is different from this half. Why? Because of the another bromine atom that is present here. So I can say this is a chiral center. Chiral center is denoted by star symbol. Now similarly, if you are looking here, here also one hydrogen atom is there, and this is also chiral center. Clear? Because here also when you try to find a symmetry, these two half are not similar. Correct? So you can draw it and ensure that. Okay, so as such we can say the two carbon atoms where bromine atoms are connected are chiral centers. Okay. So next I am going to define a new term that is called stereocenter. Stereocenter. Stereocenter is different from chiral center. Usually stereocenter is not mentioned in our textbook, but you should just know what is a stereocenter. That's why I am defining this term also. So I can say those centers, okay, those centers in a molecule, okay, which can show optical, or, very important, optical or geometrical isomerism. Very, very important. Geometrical isomerism are called stereocenters, because from the term itself you will understand. Stereochemistry or stereoisomerism include both optical and geometrical isomerism. So here we can say if you look at a carbon atom, and that carbon atom, if it is able to show either optical or geometrical, then we call that carbon atom as a stereocenter. One good example I can give you. Listen here. Look at this compound. Okay. So look at this compound. So here you could see double bond is here, and this is being connected to CH3, okay, and the other one being connected to hydrogen. Now analyze this compound. So here also one CH3 is there, okay, and other one you can see one hydrogen atom is being connected here. I will explain what is this notation and all differently. I will explain. Let's see here. Now I can say if I am analyzing this carbon atom, okay, one valency is CH3, other valency is hydrogen atom, the other two are ring actually, okay, it's a part of the ring, but we know that this ring, there cannot be a symmetry in this ring because both are different. So I can say this is a what center? Chiral center, or it is a stereo center because it shows optical isomerism. Now next one here, this one it cannot be because both are hydrogen atom, correct? Now when it comes to this carbon atom, it cannot be a chiral center because it has a double bond, but it can be a stereo center because it shows geometrical isomerism. Because in this carbon atom you can see here one of the valency is satisfied with the CH3 and other is CH2. So to the sp2 hybridized carbon atom both valencies are different, and to the other sp2 hybridized carbon atom both valencies are different. So this is a stereo center, this is a stereo center, but not a chiral center. Clear? And when it comes to here, this also you can see it's double bonded carbon, so it's again another stereo center. This is another stereo center, but this one I can say it is a what actually chiral center as well as a stereo center. Clear? So I hope this concept is clear for you. Next we will try to understand what is prochirality. This is another important term in optical isomerism. Prochirality, okay, prochirality. These terms are not there in textbook, but you should understand this. So I can say a molecule is said to be prochiral, is said to be prochiral if, okay, if it can be converted, okay, if it can be converted from a chiral to chiral, in a single, very important, in a single chemical step, in a single chemical change or chemical step, we can say. Okay, I will tell the meaning. For example, look at this compound CH3, okay, C double bond O, and you have CH2, CH3. Now I know that this carbon is not chiral. Now one valency is CH3, other valency is ethyl, but you have C double bond O is there, so we cannot define their chiral center, but we can say stereo center is possible. Okay, now if you are doing a reduction on this one through a single step reduction, I am going to do, okay, reduction with for example say lithium aluminum hydride. Now what will happen? Hydrogen will be added here as well as here. So what will happen to this one? CH3, CH, OH, and here CH2, CH3 will come. Now if you look at this carbon, one valency is CH3, other valency is OH, and this valency is ethyl, and you have hydrogen in the fourth valency. That means in one single step you are able to convert an achiral compound or achiral carbon to what actually chiral. So this is called prochirality. If a compound is said to be prochiral, then in one single step you should be able to convert this compound achiral to chiral. Then we say it is prochirality. What it is? Prochirality. Clear? These are different definitions that is used in this chapter, because these you need to understand. For example, when in question paper they may use these terms, so that's why I'm explaining all these things. Okay, now let's go to the next concept, that is configurations in optical isomerism. Okay, So you can, first one we are going to learn, that is called absolute configuration. Absolute configuration. Absolute configuration. So under absolute configuration we are mainly learning RS configuration. RS configuration. Okay, now how will you determine whether a carbon is in R configuration or S configuration? How will you do that? That is what next we are going to learn. So here, before I start teaching you that, here we need to understand one more thing. Here we need to understand the wedge dash representation of an organic compound. What it is? Wedge hyphen dash representation. Wedge dash representation. So let's see that. What is wedge dash representation? So if I am going to represent a compound, for example, see here, I am going to represent a compound or carbon. Now you can see this is I am using a wedge. This is called a wedge basically. Okay, and dash is something like this. So this is called dash. Now I can represent an organic compound using wedge dash representation. For example, see here CH3. Okay, C, H. Now here Br and OH. Now I can represent this using wedge dash representation. It depends upon me. For example, if I am going to represent it like this, okay, see here. Now you can see that here bromine, and you have here hydrogen is present, and here OH, okay, and here CH3. Okay, now I will tell what is the meaning of this wedge and dash. The wedge actually represents the bromine atom is towards the viewer. Suppose I am seeing this, I am looking at from here, so towards the viewer. That's what this wedge represents. Dash represents it is away from the viewer. Okay, and solid line represents they are in single plane. Clear? So you can represent this, you can understand like this. Wedge means it is towards the viewer, dash means it is away from the viewer. This CH3 and OH means it is in single horizontal plane. Now, so whenever you are given an organic compound in wedge dash representation, how will you determine whether that carbon, whether it is in R configuration or S configuration? That is what next I am going to say. Steps for that. So in the first scenario, always, this is the first check you need to do. Always ensure that the least priority group, okay, is present away from the viewer. What does that mean? Away from the viewer means least priority group is represented by dash notation. Now let's say I will explain how you need to assign priority. For example, now consider an example like this. Okay, now I'm giving you an example. Just analyze this one, then you will understand. So this is bromine atom. Now you have dash representation where hydrogen atom is present. Now here OH group is present. Now here CH3 group is present. Now how will you assign priority to this one? Very simple. What you need to do here is give priority based on the atomic number. So among the 4 atoms that is connected to the bond, here bromine atom is connected, here hydrogen atom, here oxygen atom, and here carbon. Who is having higher atomic number? That way of giving priority is called CIP rule. We have already learned this in geometrical isomerism when we are discussing EZ notation. So among this, the highest atomic number is for bromine atom. So that will get the highest priority 1. Now next comes in the list is after bromine, we know oxygen has the highest atomic number. So that will get the priority 2. Now next after oxygen, we will have carbon. So that will be 3. Now hydrogen will have the lowest atomic number, that is 4. Now you need to ensure that lowest priority is here for hydrogen atom. And please ensure that the lowest priority, that is 4, it always comes with the dash notation. If it comes with the dash notation, then only you should follow this condition or this first method. Okay. Now what you need to do next? You need to move from 1 to 2. Okay. 1 to 2. Okay. Then from 2 to 3. That only you should do. 1 to 2, 2 to 3. So what is the way of rotation? You can see here it is rotating in anti-clockwise direction. ACW, anti-clockwise, correct? This is anti-clockwise rotation. So please remember, whenever you have anti-clockwise rotation, that carbon, this carbon has the configuration will be S configuration. So I have taken an easier rule to remember this. Always remember RC. RC means Roman Catholics. So whenever you have clockwise rotation, C stands for clockwise rotation, then you will have R as the configuration. And if you have anti-clockwise rotation, then you have S as the configuration. Clear? This is the way to remember. Now this I have discussed. Now let's go to another example. Okay. So this the one we have discussed now here is what configuration? S configuration. Now let's see another example. Okay. Suppose you have compound like this. Okay. So you have a compound like this. Let's say this is my fluorine atom. Okay. And this is my OH group. Okay. And let's say this is my okay, let's say this is my bromine atom. I will take it bromine, and this is my chlorine atom. Okay, this is my chlorine atom, and let's say this is my CH3 group. Okay, now give the priority. You can see here, while giving priority, I could understand among the atoms that is being connected. Here carbon atom is connected, here bromine, here chlorine, here oxygen. Highest atomic number is for bromine, so this is having higher priority 1. Then next comes chlorine, so this is having priority 2. Then oxygen 3. Then only carbon, so 4. And I understood that this is the lowest priority group, and that is connected to dash, so I can apply the rule. So let's say from 1 I am moving to 2, from 2 I am moving to 3. So how it is rotating? It is rotating like this. So this like rotation, we can say this is clockwise rotation. So clockwise rotation, clockwise means what should come? R. So that means this configuration of this carbon is R. Clear? I hope it is clear for you. So I have already told solid wedges here represents bonds that point out of the, suppose this is the plane of the paper. You can think like this is the plane of the paper. Now solid wedge, it actually represents, that means the group is pointing away out of the plane of the paper. That means towards the viewer. If this is the person is looking like this, then the dash actually represents away from the viewer. This understanding is very important. Okay, so I hope this is clear for you. Now let us practice something. Now what can be the second scenario? That's what I am going to tell. In the second scenario, we can say the least priority group. Okay, least priority group. Okay, here in our case it is 4, always correct. The least priority group 4 is not present in dash, is not present in dash. That means this one, not present along with the dash. In that case, what you will do? That is also very important. Okay, so let's take some examples for that. For example, and now I will not give the groups, but I will mention it like this with the numbers I will say. Okay, Suppose here I am saying, you can see this is a solid dash, and priority for this one is 4. Okay, now you have dash is present here, that is having priority 2. Then you have 1 is present here, and 3 is prior. So this notation is after giving the priority you got like this. But here the problem is the lowest priority is present here, but that is present along with the wedge, correct? But we know if it is present in dash how to do it, but now it is present in wedge actually. So what you need to do, you need to change this to dash, first step. So how will you do that? Do an interchange between these two, because the 4 needs to move to dash, then who is present in dash 2, that needs to come here. So I am redrawing again. Now I have redrawn like this, see here. So after redrawing, so 2 will come here, and you will have dash will have now 4. The other things will remain the same, here 1, here 3. Now let's see again, do the same method. From 1 go to now you can apply, because the lowest priority group is now present in dash notation. So move from 1 to 2, 1 to 2. Now from 2 to 3, 2 to 3. So you know that it is moving in what direction? It is moving in clockwise. So clockwise means it is R. But our actual answer will be opposite of what we are getting here. Why? Because we done a manipulation, we done some change. So actual answer will be what actually? Yes. Yes will be the correct answer. So I can say this is having the configuration as yes. Understood? So that means take opposite. Whenever you are doing one change, take the opposite. Always take opposite. Clear? Is this clear for you? Now we will do questions, then you will get a clear idea. Only doing questions you will get fair idea. Now let me take an example, you need to tell me. Okay, so I am not going to represent by groups, I will put numbers anyway. So this is one dash I am representing. Now from this there is a wedge, this is dash, and you have another 2, and here 1 is present. Okay, here 3 is present. Okay, here 2 is present, and here 4 is present. Now tell me what needs to be done. So here we know that the lowest priority group is not present along with the dash, so we need to interchange it. So how we need to do? So we need to interchange. Okay, I will draw it anyway. So we need to interchange in such a way that this dash we don't need to change, because it is remaining the same. We need to interchange the 4 to here. When 4 goes here, 3 will come automatically here. So I can put 3 here and 2 here. Okay, and dash will have 4. Now do the same thing. Move from 1 to 2, 2 to 3. So in what direction it is moving? So again it is moving in anti-clockwise direction. If it is anti-clockwise direction, what will be the configuration? Yes. But since we have done the change, actual answer will be opposite of this one. Opposite of this one is R. So the answer here is this carbon has the configuration R. Clear? Now let's take another example. Something like this. See, so here you have 1. Okay, here you have 3, and here you have 2, and here you have a dash. Okay, with 4. Now also you can see here the least priority is 4, correct, and that is present in dash. So we need to interchange. Where this 4 should go, it should go to dash actually. Now it is present in wedge, so it needs to move to dash. So you should interchange. So how the new diagram will come? So you can see here. So 4 will come here, and here I will draw one wedge. Okay, and this wedge will have 1. This will remain as such, 3 and 2. Now move it 1 to 2, then 2 to 3. So how it is rotating? It is rotating in this direction. This direction is anti-clockwise direction. So that is yes. So the actual answer will be opposite of this one, that is R configuration. So I can say this is R. Clear? Now let's take one more example. Suppose you have something like this question. So 4 is present. Now you have something like here 2 is present, here 3 is present, and here you have the dash. Not dash, wedge. I will always make mistake whenever I say wedge and dash. This is dash, this is wedge, and this is dash, and this is 1. Now here if you see, all the lowest priority group is already present in dash, so we don't need to interchange it. So just to rotate it 1 to 2, 2 to 3. So this is rotating in this direction. So this is again anti-clockwise. Anti-clockwise means it is S configuration. But here we don't need to take the opposite because we have not done any interchange. So the answer here is this is in S configuration. Okay. So I hope this is clear for you. Correct. Now can we do some questions also then? I will take one question and let me tell whether you are able to do it or not. One real-time question. Okay, so let's say the question is like this. You have like this wedge is present. So here the wedge has hydrogen atom, and here you have dash is present. Dash is present with the bromine atom, and here you have, okay, let me say what you need to put. CH3 is present, and here you have OH is present. Okay, so very important. Now how we will do it? The same condition. So when I am assigning priority, this will have 1, okay, and this will have 2, and this will have 3, correct, and this will have 4. But the problem here is the 4 is present in dash, a wedge. So we need to change this to dash actually. So we need an interchange. So how we will change? The hydrogen will come here, okay, that means 4 will come here, and here I will move the bromine atom. So bromine atom will come here, so this will become 1 here, and there is no change for other one. So CH3 here, and that will have 3, and you have OH is present here, that will have 2. Now move it actually. So we know that 1 to 2 will come like this, and 2 to 3. So it is moving in what direction? You can see here, this is moving in clockwise direction, clockwise. So if it is clockwise, means it is actually what configuration? R. But we know that we made a change, so we need to take opposite of this one. So the actual answer will be yes configuration. So this configuration is yes. So I hope with this you have understood. Now we will go to the next concept, that is Fisher projection representation. So next we are going to learn Fisher projection representation. What it is? Fisher, okay, Fisher, 1 minute, it is not fish actually, sorry, Fisher projections. Fisher projections. This is also very important for exam. This was discovered by Emil Fischer. Emil Fischer. He is a German scientist. He is a German chemist, I can say. He only discovered Fisher projections. So in Fisher projections, for example, we use horizontal and vertical lines for the representation. For example, if I am representing something like this, bromine here, okay, hydrogen here, okay, and chlorine here, and fluorine here. So if this is the notation, then based on wedge dash, I can say here hydrogen is present away from the viewer, and vertical lines represent away from the viewer. So what is the next one? Vertical line, fluorine is coming. So this is also present away from the viewer, dash. Now horizontal lines represents wedge, that means towards the viewer. So you will have something like this. chlorine, and here we have, okay, here we have bromine. This is the conversion step. Now let us see, whenever you are given Fisher projections, how will you find R and S configuration? That is very important. So suppose you are given question like this: bromine, okay, this is chlorine, and you have hydrogen here, okay, and fluorine is present like this. So how will you check whether this is of which configuration? So here I am telling you a different technique rather than the other one, wedge and dash. So here what you need to do is, first thing is again assigning the priority. So assigning priority, we could understand this is 1 and this is 2, this is 3 and this is 4. Okay. So after assigning priority, you give again the same method, move from 1 to 2 and 2 to 3. So what is the direction? So you could understand it is clockwise. Okay. Now the next step is check the fourth priority group or the least priority group is present in the vertical line or horizontal line. Now it is present in the vertical line. So I can say the least priority group is present in vertical line. So we can say it is the least priority group is vertical and it is clockwise. So V vertical clockwise. Then I have a shortcut for you. Please remember this. HAR. HAR means you can say fail, correct? So here H stands for horizontal. Okay, horizontal. A stands for anti-clockwise. So that means if you have the least priority group is in horizontal and the rotation is anti-clockwise, then it is R configuration. Now we can say if the least priority group is horizontal and the rotation is clockwise, then the configuration will be opposite of this, HCS. Now you go to vertical. Now the least priority group is vertical, okay, and it is clockwise rotation. So vertical and clockwise rotation. You can see horizontal and clockwise rotation result in S. Then vertical and clockwise rotation will result in opposite of this one, that is R. Here H and C result in S means here V and C will result in R. Now similarly tell me, if it is vertical, least priority group is in vertical, and if you have anti-clockwise rotation, then what will come? Because V and C result in R means V and A will result in S. Or you can think like this: horizontal and anti-clockwise was R. So vertical and anti-clockwise will be opposite of this one, that is S. Okay. So these four things you should remember. So that's why I am just telling, please remember this one alone. Now in our case, in this question, we got V vertical, this is vertical, and you got clockwise. If it is clockwise, then now tell me what is the configuration? R. So the answer here is R. Clear? Now we will do more question to understand this. Okay. So you have a new question in front of you, like CH3, okay, CH2, and this is getting connected to CH2Br. Okay, now this is getting connected to here CH3, and here this is getting connected to CH3. Now in this scenario, now can you tell me in this one what is the configuration of this one? So here first thing is assigning numbers. So I understood that here all are carbon atoms. So after carbon atom, here this one is connected to bromine atom, then 2 hydrogen atom. Please write it in decreasing order of atomic numbers. Here after carbon atom, it is connected to 2 other carbon atom and a hydrogen atom. Please write it in decreasing order of atomic number. Here after carbon atom, it is connected to another carbon atom and 2 hydrogen atom. Here it is all hydrogen atom, it is connected. Now we know that with carbon atom we cannot find it out. After carbon atom, who is having the highest atomic number? Carbon, bromine, hydrogen, or carbon? We know it is bromine, so this is having higher priority. After bromine, we have carbon, carbon and hydrogen. So both are carbon. Then go to the next one. Here also it is carbon, here it is hydrogen. So this is having the second priority. Then we know, comparing this one, this is carbon and this is hydrogen. So this is third priority and this is fourth priority. Now move from 1 to 2. This is 1 to 2. Then move from 2 to 3. 2 to 3. I have moved. So now tell me in what direction it is rotating. It is rotating in anti-clockwise direction. Now we know that the least priority group is present in vertical line. So we got vertical, now anti-clockwise. So vertical anti-clockwise means what will be the configuration? We know vertical anti-clockwise means the configuration will be S. So I understood the configuration here is S. So the answer here is it is in S configuration. Clear? Now let's go to one more question. So this is very interesting to do actually and very important as well for exams. Okay, they can ask this question. So you have the question CH3, okay, and it is connected to hydrogen, and here you have the bromine atom, and here you have CH2, CH3. Now assign numbers to this one. So we know that higher atomic number bromine atom, so one first priority. Then you have both the carbon atoms, but here you have hydrogen, hydrogen and hydrogen. But here you have this carbon connected to another carbon and two hydrogen atoms. So comparing this one, I could understand this is having second priority and this is having third priority, and then only this one. Why? Because here carbon atom, here hydrogen atom. Now you rotate it. So we know that first priority comes for bromine atom, correct? And second priority for this one. So we say 1 to 2 and 2 to 3. So in what direction it is rotating? It is rotating in clockwise direction, clockwise. And we know the least priority group is present in horizontal. So we take horizontal system, horizontal clockwise. Now go there and see horizontal clockwise is what actually. We know that horizontal HAR. So horizontal clockwise will be HC. Horizontal clockwise will be always S configuration. So we can see this is S. So the answer here is it is S configuration. Clear? So I hope it is clear for you. Okay. Now let's move to the next concept. Okay. Suppose let me say you have a question like this. Let's take a question like this. Okay, I hope you could see. Okay. Yeah. Now you have carbonyl group here, and you have OH group is present here, and you have hydrogen being present here. Okay, now you assign the priority. Now on seeing this one, we can say the priority, again we can see wedge and dash are present together and nothing is present in between. Okay, then it's fine. Now while assigning the priority, we know that this carbon atom has oxygen connected, hydrogen connected, and this is connected to carbon, this is also carbon. So first priority goes to here 1. Now the next priority means here carbon, here also carbon. So this has carbon connected to one of the valency to here another carbon, here also connected to another carbon, but here this carbon being connected to oxygen, but this one you can see it is connected to only single oxygen, but this is connected to double bond, or means that means connected to 2 oxygen atom. So we say this is having priority 2. Okay, then this is having priority 3 and this is having priority 4. So after seeing this, we could understand the least priority is present along with what? Dash. So there is no issues. We don't need to interchange anything. So move from 1 to 2, 1 to 2, then from 2 to 3, like this. So we could understand it is moving in what direction? Clockwise direction. Correct? So since it is moving in the clockwise direction, so you know that this will be RC. Correct? Clockwise means its configuration is R, since it is wedge dash. So the answer I got it as, for that particular chiral center, the configuration is R. Clear? So next comes here is actually we will learn some of the basic definitions that is present here. So the first one that we need to learn here is what do you mean by enantiomers? Okay, we will see that one by one. Okay, as I told, we are going to learn some of the fundamental terms in optical isomerism next. So the first in that list is enantiomers. Enantiomers. Okay, so what do you mean by enantiomers? We can say non-superimposable. Superimposable means you cannot put your right hand on top of your left hand. It will not match. That is called non-superimposability. Non-superimposable mirror images. Mirror images are called enantiomers. Very, very important. Okay. Now, for example, I can represent this one. For example, you have a wedge dash representation, CH2, CH3, okay, and you have a bromine present here, bromine, and you have a dash present like this, hydrogen, and you have one of the wedges present here. Okay. Now you have CH3 is present here. Now how I will draw the enantiomer of this one? Take the mirror image. We know that mirror image of ours will be left and right inversion, not upside down inversion. So if you take the mirror image, what will happen? This hydrogen will come here, correct? So you will have, listen, you will have hydrogen like this will be present, and you have CH3 will be present like this. Okay, then you will have bromine will not change because it is present in upside direction, and the CH2 CH3 will be like this. So these are mirror images. So we can say non-superimposable mirror images are called enantiomers. So I can give you another example as well. Let's see this one. This will give you more clear idea. Suppose you have a compound represented with Fisher projection denotation. Okay, you have CH3 is present here. Okay, and you have hydrogen present here and OH being present here. Now how will the enantiomer looks like? So I can draw the mirror image of this one. On seeing the mirror image, OH will come here, correct? So you will have H, O and hydrogen, and there will be no change in the upside down direction. So COOH and CH3. And if you try to take this diagram and put on top of the left one, it will not superimpose. So we can say these are non-superimposable mirror images. So these are enantiomers. Clear? Now let's see more examples. So if you see its optical activity, they have different valencies satisfied here. So we can say one of the important properties, like properties of enantiomers, like this. Note down, enantiomers, okay, are optically active substances. They are optically active substances or compounds. They are optically active substances, and they have identical physical properties. They have identical physical properties. And other important thing is, now if I take an enantiomer, you could see if this is rotating the PPL towards right, maybe say for example 10 degree, this will rotate the PPL towards left towards the same 10 degree, because these are mirror images, correct? So we can say they rotate the PPL, they rotate the plane polarized light PPL, okay, in opposite direction. in opposite direction, but to the equal extent. Correct? Because if one is rotating 10 degree, other will also rotate in 10 degree, but in anti-clockwise direction. Equal extent. Very, very important. So next we will try to see the term diastereomers. What is diastereomers? Okay, diastereomers. Diastereomers. So we can say stereoisomers which are not mirror images. They are called diastereomers, which are not mirror images. So better way to learn this one is I will draw a set of compounds and you need to tell me how these are related. Okay, so let us see. I am drawing a compound COH. Okay, and you have a CH3 present here. Okay, you have H and OH present here. Okay, and here also you have H and OH. Okay, now you have another compound COOH. Okay, here CH3 present here, and you have I can say H is present here and OH, and OH is present here and H. This is compound 1, this is compound 2. Okay, and you have another compound 3, COOH here. Okay, and you have OH present here and H here, OH and CH3. Now let us analyze this one and say, here if you see how 1 and 2 are related. So if you see 1 and 2, if I take the mirror image of this one, here OH should come, but here it is H. Here OH is there, but it is not the mirror image of this one. So I can say 1 and 2 are diastereomers. D. I will use D. Okay. Now let's say 1 and 3. I am comparing 1 and 3. So take the mirror image. So here OH, here also OH, no issues. But here OH, but here it is H. So that means they are not mirror images. So I can say 1 and 3. They are again what actually? Diastereomers. Now I am going to say 2 and 3. 2 and 3 I am taking here OH. So here mirror image, this should be OH. Here H, here should be H. Yes. So these 2 and 3 are mirror images. Correct? 2 and 3 are mirror images. So I can say 2 and 3 are not diastereomers, they are enantiomers. Clear? Very, very important. Okay, now let's see more examples to understand the same. Okay, then you will get a clear idea. So I am going to give you 4 figures like CH3. Okay, then you have CH2, CH3. Okay, then you have HCl present like this and another HCl present like this. This is my diagram 1. Now you have another diagram Cl hydrogen, and you have Cl hydrogen, and you have CH3 present here, and here CH2, CH3. This is my diagram 2. And next we have CH3, and you have here CH2, CH3. So you have HCl present here and you have CLH present here. This is 3. Now you have the 4th one, CH3, and here you have CH2, CH3. Okay, you have CLH and you have HCl. This is 4. Now you need to comment on how each are related. Let's say 1 and 2. 1 and 2. How they are related. So if you take the mirror image, what will happen? Cl will come here, Cl will come here. So it's a mirror image of this one. So I can say 1 and 2 are actually what? Enantiomers. E. Now let's go and take 1 and 3. So 1 and 3, see here, 1 and 3 is here. So if I take the mirror image, here Cl should come, but H is there. So that means 1 and 3 are diastereomers. Now let's go and take 1 and 4. 1 and 4. So Cl is present, Cl is present. So I take the mirror image, Cl is present, no issues. But here I am taking the mirror image, here hydrogen is present. So that is different. So we say they are diastereomers. Now let's say 2 and 3. 2 and 3 let's take. So if I am take 2 and 3, take the mirror image, here hydrogen, no issues. But here hydrogen, here chlorine is coming. So that means 2 and 3 are diastereomers. Now let's say 2 and 4. Okay, 2 and 4 if I am comparing, take the mirror image, here hydrogen, but here chlorine. From that itself I understood they are diastereomers. Now we will take 3 and 4. 3 and 4. Okay, 3 and 1 and all we already done it. So 3 and 4, let's see, take the mirror image, chlorine, here chlorine coming, here hydrogen coming. So it's a mirror image, correct? So we can say they are enantiomers. This is how we can say whether the given compound is a diastereomer or an enantiomer. Now next we are going to learn a separate class of compound, and you might have noted one thing here. Here CH3 is present, but here the group is different in all the examples I mentioned. Now we are going to learn a next set of definition, that is called a meso compound. Okay, meso compound. So meso compound, we can say compounds, please write down the definition, compounds having at least two chiral carbons, okay, and a plane of symmetry. 2 chiral carbons and a plane of symmetry, very, very important. And a plane of symmetry is called a meso compound. They are optically inactive. Due to internal compensation, very, very important. Due to internal compensation. I will explain. Please listen. Suppose you have a compound like this, COOH. This is called tartaric acid. Okay, COOH, and this is COOH, and you have HOH is present here, and HOH is present here. Now if you see this compound, you can say, if you look at this carbon alone, we can see it is hydrogen, it is OH, and it is COOH, and the fourth valence is some big group. So this is chiral. And if I look at this carbon, this is hydrogen, this is OH, and this is COOH, and this is some big group. Next, so both carbons are individually chiral, but the problem here is there exists a plane of symmetry, that if I divide this compound using this plane, both halves are identical. That means if this chiral carbon rotate the compound in right hand side or maybe clockwise direction, then this will rotate in anti-clockwise direction to the same extent. So that means the plane PPL will get rotated both in the right hand side as well as left hand side to the same extent. So it will get compensated. As a result, this becomes optically inactive. So this type of compensation is called internal compensation, optically inactive. Okay, so as such, so if you take this compound as such, this will be achiral in nature, but individually these carbon atoms are chiral. Clear? But there is another compensation called external compensation. Let me tell that also. External compensation, we have already learned that, we will tell. In external compensation, I can say there are two compounds are there. Okay, so maybe we say dextro and levo. The one compound will rotate the PPL towards 10 degree in clockwise direction, and other compound will rotate in anti-clockwise direction to the same 10 degree. So here this is getting compensated. So if this mixture or this organic compound has, let me say this is mixture 1 and this is mixture 2. So mixture 1 and mixture 2 are present in equal quantity. This is 50% and this is also 50%. Then what will happen? This will 50% will rotate in 10 degree, other 50% will rotate in minus 10 degree. Again, the net compensation is equal to 0. So I can say as such this compound is optically inactive. But the important condition is optically inactive. But the important condition here is they should be present in same amount. But if so, such a mixture is called a racemic mixture. Such a mixture where both dextro and levo are present in equal amount and they will rotate in opposite direction, and they are called racemic mixture. Dextro plus levo in equal amount. Suppose this is in 75% and this is 25, then means 75 will dominate and it will rotate the PPL towards one direction. Clear? So I hope external. So please remember, racemic mixture is optically inactive due to external compensation, and meso compound is optically inactive due to internal compensation. Very, very important. Clear? So I have tried to explain these things. Now let's take one simple example and see. So suppose you have a compound like this is given. So can you tell me whether this compound, this is we are taking cyclic compound and seeing whether this is optically active or inactive. I hope I have already told this. So you can see here one valency is hydrogen, one valency is CH3, but we can see the other two are present in a cyclic compound. So check here whether plane of symmetry is there. Yes, these both halves are equal. So that means this is optically inactive. Optically inactive, or it is achiral. Now let's take another example. Look at this compound. Okay. Now you have chlorine and here CH3 is present. Now see here this carbon, one is chlorine, other is CH3 and other is present in a ring. But if you try to divide this compound, you have first half that is different from the second half. So I can say this is chiral, or it is optically active, OA, optically active. Clear? I hope this is clear for you. Now next we will see in double bonded compound or in double bonded Fischer projection system, how we are determining the R and S configuration. This we will see in the next class. Thank you.